Thank you. Thank you for the introduction. So yeah, today I'm going to talk about the cryptanalysis of the problems that we introduced yesterday. So you can see this talk as either continuation or complementary talk. Nevertheless, I will still start with some preliminaries, so you can still see it as an independent or as a recalling what we saw yesterday. Then I would like to continue with decoding algorithms, in particular two classes of the decoding algorithms that are proved to be the most effective and the most efficient in the code-based setting. So the first class is called the information set decoding, and that's actually a very long line of different research that was done on these decoding problems. And yeah, you can see this part as evolution of the information set decoding algorithms. And then I'm going to talk about the statistical decoding, which is a kind of very different approach to solving the same problem. And so the information set decoding I have worked on. So in that part, I welcome your questions a lot. So it would be very, very nice to have some discussion on this part too. Statistical decoding I have never worked on, so I'm familiar with it. I hope that I will be able to answer the questions, but yeah, please do ask them. Okay. So let's start with first recalling what we talked about yesterday. I would like to start with the definition of the linear code. So yesterday we saw that we can define the linear code using the generator matrix G, that is some matrix of size k times n, with entries from the finite field of size q. And so it basically defines a linear code that is a linear subspace of the fq to the n. And it is given as all the code words in fq to the n that are obtained by multiplying the message with the generator matrix, where the message comes from this space fq to the k. And as I have mentioned, so linear code is basically a linear subspace of fq to the n. And the parameters of the code that are very relevant for our discussion are the code length, basically the size of the space to which we are encoding to, so the size of the larger space, k, which is the dimension of the size of the space in which we have all the messages. And finally, one parameter that maybe I have mentioned yesterday, but I definitely didn't speak about a lot, is the so-called minimum distance of your code. So that's basically the distance between the two closest code words in your huge vector space fq to the n. And this value is a very important parameter of your code because it basically tells you what is the error correcting capability of your code. So if your minimum distance between the two code words is very small, that means that everything that falls in between these two code words, it will be actually hard to decide to which code words it's the closest to. So this parameter is going to play a very also important role in deciding how we design our problem and how we decide on the parameter regime where our problems are hard. Okay? So that's about the linear codes. And then, so again, we need to decide how to actually, formalize this notion of a distance. So within our real life, so notion of a distance is commonly known as the Euclidean metric, and that's something that is very intuitive. In the code-based setting and in the coding theory in general, so Hamming distance is something that we normally observe. And it is defined, so the Hamming distance between the two vectors, so in this case, C and C tilde, is defined as the number of positions in which these two vectors actually differ. And from that, we can also derive the definition of the Hamming weight, which is basically just the distance between the error vector, in this case, and the origin, or any vector and the origin of the space. Or equivalently, you just count the number of non-zero positions in your vector. Yeah, so far so good. I think that that's probably something that you might have known already before these talks. So now, the code word finding problem is a problem that is derived from the most intuitive way of decoding your noisy code words. And yeah, we defined it already yesterday, but let's recap. We are given as an input a generator matrix G of a linear code C, a noisy code word C tilde, and the distance W, that is some integer value that is not greater than n, actually the dimension of your code. And we are asked to find the code word C that is in our linear code such that the distance between C and C tilde is not greater than W. And as we mentioned yesterday, so this problem would be very easy if we don't have like one of these constraints. So if our code word is not actually in the code, but anywhere in the space and has the Hamming weight W, so it would be an easy problem. Also, if the code word is in the code, but we don't have this like a weight restriction, this would be, again, a very easy problem to solve. Now, the equivalent version, so syndrome decoding problem, we are given a parity check matrix H, a syndrome S, and the weight W, where W is, again, something that, some integer value that is smaller than the code dimension. And we are asked to find the error that satisfies both the syndrome decoding constraint. So once the error vector is multiplied with a parity check, it should yield the constraint. And the weight of this error vector should be no greater than W. And this problem is going to be more relevant for today's talks because like most of the techniques are focusing actually on solving this type of problem. What we have also mentioned yesterday, that these problems are NP-complete. And I highlighted yesterday, that does not mean that this problem is good enough for your purposes. So it just like gives you a good intuition that it might work because you have like this asymmetry. So it's very hard to find a solution, yet it's very easy to verify it. So somehow it gives you a natural approach to create some of the, like for example, encryption system. But nevertheless, we need really to show that these problems are actually hard on average. And showing formally that these are hard on average have not worked for us quite well so far. And the approach we normally take is actually to design the algorithms that are going to attempt to solve these problems, hence cryptanalysis of the problems. And in that case, we can say like what is the best we can hope for with our currently available algorithms and like, yeah, with our computational power. And yesterday I mentioned like that there is conveniently chosen parameters. And what I meant by that is actually that we have like parameters that actually promise us that we will have like only one solution to our decoding problems. And today I'm also going to stress that actually we can formalize that by saying that we are in the full distance decoding regime, where actually this parameter the parameter W is actually equal to the code distance of our code. So the minimum distance to the between the two code words. And yeah, what we know about this, so these like type of the problems in the full distance decoding regime are hard for both classical and quantum algorithms, so they require some exponential time in the input size. And yeah, therefore we believe that they are post-quantum or quantum resistant. And as such, they are used as basis of both ghost-based and lattice-based primitives that we talked about in the last couple of days. But you can even like provide some analogies between also the multivariate primitives and also the multivariate problems. Okay, so that was about the recap. So any questions like on this part, also on the part of yesterday? So anything that is unclear? Okay, people still not awake. So now let's move to the algorithms that are trying to solve these problems. So as I mentioned, so we are trying to determine how hard our problems are in the real life environment, or like this is still slightly more theoretical environment, but assuming that we are like the best possible like cryptanalysts in the world. So we design the best possible algorithms. And in that case, like we can trust that our like computational power that we have right now cannot break certain type of problems. And what we want to show now is that what would be the like correct parameters that we need to choose for this type of the problems so that we can guarantee certain level of security. So, and that's where the information set decoding comes in. So it's the set of the best generic algorithms for decoding problems in the Hamming space. So I'm highlighting that it's in the Hamming space because like in the Euclidean space and in the case of the lattice-based cryptography, it's slightly different. So the approach would be slightly different. There are some similarities, but it's not exactly the same. So in this type of, in this approach, in this type of the algorithms, search for a solution is done directly. So you're searching for a solution in the code. So this is known as the category of the primal attacks. And so it can incorporate different subroutines. So during your algorithm, you're basically creating a sub-instance of your syndrome or code word defining problem. And you're trying to solve it using different subroutines. And in particular, we will see the one approach or like one type of the subroutine that is based on the collision search. Or maybe you have heard of the birthday search or birthday paradox, meet in the middle, something. I hope that something rings a bell. So then we will also see near neighbor search, and that is something that can be defined slightly different in different areas, yet it's referred to very well-known problem of finding like two vectors that are close to each other in some vector space. And here I'm going to represent, so here I'm going to just explain how they're incorporated into this like information set decoding framework. Nevertheless, it can be also seen, so this type of algorithms can be slightly differently defined for different purposes and can also be seen in some other domains. Like for example, machine learning also has near neighbor search, and it's a related problem, but the techniques to implement them are slightly different. And finally, I will explain so the sieving techniques that are related to the information set decoding and in general code word finding problems. So sieving you might heard of before also in the number theory sieving. Yeah. So it's quite different type of sieving from this one. Nevertheless, the approach is kind of like the high level idea can be seen somehow like very similar. And yeah, I'm going to explain how we can use it in the information set decoding framework. One interesting thing about the information set decoding is that it comes both in classical and quantum flavors. But in the classical flavor, in the classical development of the information set decoding, we have like many algorithms. So I'm going to cover some kind of evolution of these algorithms, but still I will like skip over many algorithms that are still there. So if you're interested, there is like still like some research and reading to be done on this topic. In the quantum part, like the algorithms that I'm going to present there today are almost everything that you have there. There was some generalizations of these approaches that I'm going to present, like in some attempts to improve them, but there was not that many things that were going on in the quantum information set decoding thing. So I would also encourage you, if you're interested in the quantum algorithms, to think about this, working on this topic. Okay. So let's start with the framework itself. So I'm calling it a framework because there is like many algorithms that fall into this template. So information set decoding takes as an input a binary linear code. It can be described either via parity check matrix or generator matrix, a noisy code word C tilde, weight W, and two additional things. So one is a parameter capital N that I will explain in short. And the other one is the oracle. Yeah, I'm calling it as an oracle because it sounds fancier, but in fact it's like basically a choice of the subroutine that you're going to use or the algorithm that is going to solve your subinstance. And then we are given so we are searching for a code word that is in the linear code C that satisfies this distance constraint. So the distance between C and C tilde should not be greater than W. Okay. So that's just like the description of the problem. And now we start our algorithm and we actually repeat it while we don't find a solution. So one very important thing to do here would be actually to show that this algorithm ever terminates, so that we have like high enough of probability finding a solution in one iteration. Otherwise, this algorithm doesn't make sense. I'm not going to talk about that much about these probabilities, but there is actually a way to calculate them explicitly, and so it's not like that we are just running the algorithm and just hoping for the best that we will find a solution at the end. So then we start by guessing part of our solution. And this guessing is something that Monica has already described as a brute force attack, the most natural type of the brute force attack, in which you just say, okay, so I have a code word, and I will just guess a certain number of its positions, and I will say there is no errors. And this is exactly the approach that was taken by the first information set decoding algorithm. And what we do that way is basically we fix certain positions. We say there is no errors, and the rest of positions are actually giving us the subinstance of the new problem that is of a slightly smaller dimension. So part of your code word is guessed, the rest you need to somehow find a way to solve. So basically, the rest of your code word is now smaller. Also, the parity check equations that are, or the generator matrix equations that you are checking is also slightly smaller. So the matrices are slightly smaller. And the parameter of the weight will be also adjusted depending on the algorithm. So you're basically creating a new instance of the syndrome decoding problem. And this instance is smaller. And what is also important about this instance is that in this case, that you can find many solutions to this smaller subinstance, because we are starting from the instance of the problem for which we know that we are in the regime where there is only one solution to your problem. And in the case of the subinstance, we know that there is going to be many solutions, potentially like a lot of them. And this first step, so just the guessing part, can be done in polynomial time, so it's not expensive at all. Then we solve this subinstance using some subroutine or like the Oracle A. And for this part, so this part can actually become very heavy. So it depends on the choice of the like algorithm you are using. So I will just denote it generically by TA. So it can be like anything depending on your the choice of your subroutine. And finally, once you obtain the solutions to your subinstance, you want to check if they lead to a solution to the full instance. So now you want to actually check if your guess at the beginning was correct. So do you have like the solution for the full problem? Okay. And since we know that like this like subroutine actually gives you capital N solutions, this is the parameter I introduced at the beginning. So this, yeah, maybe like this, it's better. So this capital N will be actually the number of solutions that you obtain when you're solving the subinstance of your problem. So checking them would take time that is like number of these solutions, which is capital N times poly N, because the checking can be done efficiently. So that leads us to this like to this running time. An important thing to say here is that this like capital N, of course, it can be many solutions, but for the reasonable choice of parameters, it's not going to be greater than polynomial in N. So this whole step can be seen as like something that is efficient and runs in polynomial time in N. Okay? Yeah?
Why did you say first that there is one solution for the initial instance?
Yeah.
And then when you're fixing, when you're making guesses, there's more solutions?
More solutions for the subinstance.
Okay. I thought intuitively you're not relaxing the constraints.
So yeah, but so the difference is that now you're having a smaller instance, so you don't need to. So you're taking certain like constraints from your parity check equation. So you're creating a smaller system of equations that have potentially more solutions.
You're just removing columns, right?
Yeah, you're removing columns, and so depending, of course, on your choice of like how many like of columns you are taking,
And then W is bigger compared to your instance.
Exactly. So that's also a very important thing that we are going to discuss. Like, how do you choose then like the number of columns that you can take afterwards? So this like weight. So now we are going to have like some W prime that is relevant to our subinstance, and this W prime dictates the number of potentials, the number of solutions we will find in the second step. Okay. Yeah.
When you check the subsolutions and you say none of them are actually part of, like none of them are a good solution or an actual solution to the main problem. When you then loop, how do you make sure that the new problem, like the solution set of the new subinstance, doesn't overlap with the solution set of the old one?
It might. So it might overlap. But so if you're guessing like different parts of your information set, so if you guess different positions, it will not fully overlap. So there might be some like solutions that you have checked in the previous step that has failed. You don't record them because it would require too much of memory. You just like continue as if you didn't know anything about the previous iteration. And this.
Make someone sure that like the overlap isn't too big.
Well, so if you're assuming that you're sampling randomly this information set, so it will not happen with the overwhelmingly high probability. So one thing that I have not mentioned here, so guessing the information set is basically guessing k positions in your like code word. And that's why it's called the information set. So these k positions should like correspond to the positions in your code word that correspond to the original message. And so if you're sampling k positions, then like this overlap should not be too high. Yeah. And you can also take it into account in the like when you're calculating the probability of like succeed in one iteration, if you have like some correlations in between, but yeah, I'm not aware of any algorithm that was actually trying to use that information in different iterations. So maybe it would be actually interesting to explore that. Yeah. Okay, some other questions? No. Okay, so then let's see what is the running time and the memory of this algorithm. So yeah, as I mentioned, and as you have seen in the slide here, so basically these two steps are not costly. So we'll like just assume that this capital N is not like very large, so it's like at most polynomial in N. So these two steps, in some sense, can be seen as a very efficient. And this step is something that is like computationally heavy. And using this O tilde notation, we are actually like somehow managing not to see all the polynomial factors. So the running time will depend only on the running time of this subroutine, as well as on the probability first that we guessed the information set correctly. And then again, the probability that the solution to the sub-instance actually gives you a solution to the original problem. So this actually corresponds, so 1 over P1 times P2 corresponds to the number of iterations that will guarantee us that we will find solution with overwhelmingly high probability. Of course, it might sometime, in practice, it might require more iterations, but at least we know that we don't need to run our algorithm forever. That's a very important part. Regarding the memory, again, so the only like memory intensive part is actually this part here, where we need to store our solutions. And the good news is that like since we are not like having any kind of connections between different iterations, we can reuse the same memory every time. So the memory that we use in our algorithms is dominated by this part. And I'm not going to talk about memory that much today. It's also a relevant topic, but I was mostly focusing on the running time because people are trying to improve this running time as much as possible. But memory is actually a very important consideration. And especially in the quantum information set decoding part that I'm going to talk about later, every improvement that you make in the runtime domain actually leads to huge like overhead in memory. So memory is something that you should definitely think about when you think about these algorithms. Okay. So yeah, what we know, that is that the computational complexity of these algorithms is exponential in the input size. So we don't hope for much better than that. I mean, it would be very nice, and like for the optimistic people, it might be also very useful to take that approach that you can actually improve and obtain something that is at least sub-exponential, but people tried and failed. So yeah, what we believe now is that all these algorithms are always going to run in exponential time, so we are just trying to improve this exponent. And improvements in different, as I said, I'm going to describe the evolution of these ISD algorithms, but what these improvements focus on is actually balancing the trade-off between the cost of one iteration and the probability of success in one iteration. So when you balance out these two things, ideally you would obtain that the cost of one iteration is exactly the same as the probability. In this case, you have constant time. It's not going to happen, but as close as you can get in this trade-off, that would lead to a better algorithm. And I would now like to give you examples of different classical ISD algorithms. And as I mentioned, this list is far from full list of all the possible ISD algorithms. I'm just going to try to introduce technique by technique, the way it was introduced chronologically. And at the end, I would comment on the complexities of these algorithms. And I decided not to put all the formulas that you might have expected at the end of each algorithm to argue that something is better or worse. But as you go toward the more sophisticated ISD algorithms, these formulas become very hard to parse. So I don't think they are very informative. So at the end, you will just have the comparison on the numerical results on the running time of these algorithms. Okay. So let's start with the chronologically first algorithm and the simplest one. It's called Pronge. French people would pronounce it as Pronge. I think German people as Pranga, American, US, UK people as Pronge. So take it the way you want it. I will pronounce it as Pronge. So that was the first algorithm in the family of the ISD algorithms. it's, as I mentioned, it's the simplest one. So its oracle basically does nothing. So it just like creates one solution and then we check it. So it's a very simple way to perform this task. In fact, we are just basically guessing the full solution to our problem. And then we are hoping for the best. And what is a very nice thing here is that leads to an algorithm that requires almost no memory. That's a very good thing. Nevertheless, the running time is not ideal. And the first, maybe I will start just like by giving you like one graph of this the complexity of the Pronge algorithm, because this is the way how these like curves look like when you normally compare different ISD's algorithms. So they will all have this shape that looks like as a kind of an entropy function. So what we see here is that we fixed the weight so that we are in the full distance decoding regime, and then we observe this problem for different code rates, basically different proportions between the code dimension and the code length. And then what I plotted here is basically just the exponent of the running time. Okay? And so whenever you plot it, it will always have this shape of the curve. And so all the improvements that will come will probably come in some part here, closest to the peak of this curve. And I'm going to present at the end just the comparison of these peaks for different algorithms. Okay, it's just to remember this curve whenever you see it, you know we are talking about the ISD algorithm. Okay, so the first improvement over this very basic and the first algorithm came from the idea of the Lee and Brickell that managed to create a non-trivial instance of the problem, or they use non-trivial oracle to solve the sub-instance of the problem by just guessing the part of solution. So now instead of guessing the full solution, you're just guessing certain positions, and for the rest, you have actually a reason to try to solve them using some oracle A. And in the case of Lee and Brickell, this oracle A is also not very complex. So you're basically just exhaustively search over all the possible error vectors of a certain weight. So let's try to see how, I try to depict it this way. So you created a new, a small sub-instance of your problem that I will denote by H prime and E prime. So you're just taking some columns from your parity check matrix, and also you're just taking certain positions of your error vector. And then you fixed some parameter P that is going to be slightly smaller, or in general smaller than W, so that because you're assuming that if you're not observing the full instance of the problem, you will not have the full solution and all the weights in this small sub-instance. So this parameter is no greater than W, but most of the time it's actually smaller. And then you're asking for a vector E that will solve the sub-instance generated this way using H prime, E prime, and S prime. So this is also certain positions of your syndrome. And you're basically iterating over all the possible solutions, or all the possible E primes that are of weight P, and that are of dimension K prime. And this K prime is commonly taken to be exactly the same as the original K, so your dimension has not changed. What changed is actually the code length. Okay, so you're basically searching through all the possible E primes, and then at the end you're checking if any of this E prime actually gives you the E that is the solution to your full instance. Okay, I hope this what refers to this kind of a brute force search to this problem. Okay, nevertheless, so this idea was useful, but it has not it has not given us significant enough improvements. So it just gave some polynomial improvements that in this O tilde notation you would not even notice. So it was not considered to be very significant algorithm from that perspective. So it was not state of the art or something similar. But still it gave rise to new algorithms that are based on the so-called collision search. And the first in the line is the so-called Dummer's algorithm. So some people might have also heard about Stern algorithm. It's very similar in spirit to Dummer. So I will just describe Dummer. So it was the first significant improvement. Actually, it gives this improvement in the exponent. And it uses the so-called collision search and the Shopper-Shamir approach. And yeah, if you have never seen this like Shopper-Shamir approach, that probably means that people just try to avoid to pronounce these names, because every time were creating like Stern or Doomer-like algorithm, that's most of the time it's used also, like this approach is also used to create this type of algorithms. And what do I mean by that? So now what we have, that instead of like just trying to like solve the full instance, actually the full sub-instance of your problem, you're splitting your solutions into two parts, E1 and E2. And each of these two parts is supposed to now be of the weight P over 2. And so in the case of the like first list or like E1, what we have is that all the weights are actually on the right side of your vector. And in the case of E2 or the list L2, all the weights are on the left side of your list. So once you sum them up, so once you sum E1 and E2, you will actually get a vector of weight P. So it will lead to the same type of solutions as in the case of Lie-Brickell. But why would we do this? So first thing, so the list we create this way, so the number of E1s that we can have this way is significantly smaller, because it basically corresponds to the number of vectors that are of length k over 2, k prime over 2, and weight p over 2. So this list is significantly smaller than the previous one. That's the first improvement that we get. And the second thing is that, yeah, in this picture, it was like too crowded if I also added a collision parameter that we are using. So we are not trying to like find E's that satisfy the full syndrome decoding constraint, but just like part of it. And this part is going to be denoted by C, that you can see here. Like it's not even that tiny. I was worried about that. So this parameter C is basically the number of the positions on which you're colliding your syndrome on. So, and this thing is going to be very important because this parameter is going to determine actually how much you gained through your collision search. And what we obtain using this approach is that like the number of the solutions that we will find to our sub-instance will surely decrease in comparison to Lie-Brickell. Nevertheless, this type of search is significantly more efficient. So this trade-off between the probability of finding a solution at the end and the running time of one iteration now shifted more towards so the probability increased, but the probability decreased, but the running time has also decreased. So you have like overall improvements that can be seen in the, like if you analyze the exponents of this algorithm. Okay, maybe I will give you just a second to think about it because, yeah, it's pretty condensed information, what you have here. But the general idea is that instead of like creating like one list that you're going to brute force search in your sub-instance, you are creating two lists of the vectors of slightly smaller weight. You separate these weights on the left side and the right side, and then you merge them on a certain number of positions of your syndrome to obtain finally the list that is going to be explored in the last part of the ISD algorithm. Okay. And if you thought this was complicated, it can go worse. So there is even generalization of this type of the problem. So using the so-called generalized birthday problem by Wagner. And yeah, so Wagner definitely didn't think about like ISDs when he created this. It's like just more like it was a lot more general techniques. But in a sense, it generalizes this approach of like merging and combining this like Shamir-Shopper idea and like managing to somehow perform some kind of divide and conquer. I'm not going to like give the running time of this type of the algorithms because it does not improve that much over Stern and Doomer. But the importance of this approach is actually that it can be very well combined with everything that comes after. So all the most advanced algorithms of the ISD that I'm going to present today, state of the art, they are all using this kind of like, multi-level merging and the search. Okay? So now we are coming to something that is scary in every possible field when you mention representations, like representation techniques. So I don't know if you have heard of this before, but yeah, in general, so it's like the representation techniques that are used like in this called MMT and BGMM algorithms are something that is also like technique that is used also outside of the field of cryptography. But in this particular case, so the authors used the representation techniques for solving the subset sum problem that is very connected to the code word finding problem. And yeah, this is the given by the authors that I'm afraid to pronounce the surname of. So Zhu I know, but like Hovergraph and Graham. So these are the people that actually introduced these representation techniques for the subset sum problem. And then Becker et al. Used these representation techniques to advise about the ISD algorithms that can use them. And the key insight for the later paper, so BGMM1, is that in fact, so by observing that 1 + 1 is equal to 0 in F2, which is somehow very unsurprising, you can basically increase the number of representations of your solutions to the sub-instance. And that way, you don't need to search through so many of them in order to obtain higher probability that you will find a solution to the original problem. So this is very vague description, but I will not go into many details because the algorithm itself is not very easy to be presented. But what is important to say about this algorithm is that it's actually the de facto state of the art. They are using the representation techniques and multi-level merging that we saw before. And they obtained the algorithm that is now used as something that you would implement in practice and that you will use as something that will provide you with the parameters of your decoding problems that guarantee certain level of certain level of security. So this is something that we commonly use in practice. And yeah, I encourage you to actually check the paper to see how it was designed. Okay. And one before the final technique that I'm going to talk about today is the near neighbor search, where we use the near neighbor search for solving the sub-instance of the problem. It's again combined with some of the previous techniques, and especially in the paper by May and Ozerov, it was combined with the Stern-Dummer and as well as BGMM. So what we are trying to do here is within solving our sub-instance of the problem, we are implementing another subroutine that solves the following problem. So near neighbor search, as I defined it here. So we have two lists, L1 and L2, and the elements in this list should so they might satisfy some additional constraint, but let's say these are just arbitrary elements from F2 to the N. And we have some fixed distance, and we are searching for element in X, in L1 that we will denote by X, and element in L2 that we will denote by Y that are at the Hamming distance D. And so there is different techniques to solve this type of the problem. The one that is presented in May Ozerov is not the very basic one, but it was not the most advanced one. So this type of approach actually gave some asymptotic improvements, but yet it was not beating the BGMM approach that we had before. But it was very important in the sense that it actually led to some new algorithms, in particular the Boat-May algorithm, that combined all the ideas more or less that we saw before and used advanced version of this neighbor search, near neighbor search to obtain the best asymptotic ISD algorithm. And I'm highlighting here that it's asymptotic because in the end, it was not performing so well in practice. So when you implement it, there is huge polynomial overhead. So this type of algorithms are almost never used to analyze to optimize your parameters of your problem. Nevertheless, it's considered to be state of the art for the ISD in that sense. Okay, almost there. There is one more thing I want to talk about, and it's because I worked on that, so I'm very happy to share the sieving technique. So it was introduced in the paper by Guo, Johansson, and Nguyen. And as I mentioned, so sieving here is slightly different from number theoretic sieving that you might have seen before, but there might be some similarities. So in the case of the code sieving that Guo, Johansson, and Nguyen introduced, they observed that basically we can use this type of technique to solve even the full instance of our problem. So we are now assuming that maybe we can be even outside of our information side decoding regime. So we are just given an instance of the problem. And we are asking to find n capital N vectors of weight W, assuming we can do that. So we start from capital N vectors of weight W that are not necessarily in the code. And what we want to obtain at the end is actually capital N vectors that are in the code. And if we would just do that like regularly, just performing like some Gaussian elimination as we discussed earlier, it will be very hard actually. So if you just try to start from N vectors, add all the code constraints at the same time and ask what is the list as the output, this would be like as hard as the code word finding problem. Nevertheless, what we can do is instead try to do that like iteratively. So you can imagine that every like parity check column and the related position in the syndrome actually gives you one code constraint. So you can try to add them iteratively. And each time you do that, so you start from like N vectors that are of weight W. So you can also imagine them like geometrically as vectors on the sphere of radius W. And then when you add one code constraint, you basically cut like the number of these vectors in half, because like this syndrome can be equal to 0 or 1. So adding one code constraint will basically cut half of your vectors. And then what you need to do in order to keep this like loop invariant that in every iteration you still have like a capital N vectors, you will need to add some new vectors. And this is the idea, and this is the point at which the near neighbor search comes as the subroutine for creating new vectors that are of like at a distance W, or like equivalently the new vectors that when they are combined are giving the, like a vector of weight W. Okay, so this is a bit hard maybe to follow, especially without the picture. But the reason why it is called sieving is that because you start with like just satisfying one like of the constraints of your problem, which is in this case the weight constraint, and then you're sieving so that you finally obtain the vectors that are also in your code. And in every iteration, you are basically sieving out those vectors that are not in the code anymore. So that's the reason why it's called sieving. And yeah, this like original idea was given in this paper that I have mentioned. Nevertheless, it was, it didn't lean, yeah, maybe I was waiting for too long. So yeah, this original idea did not lead to any like breakthrough in the information set decoding. Nevertheless, it like gave actually a starting point for the new algorithms that used more advanced near neighbor search techniques. And then you combine that with the sieving oracle in the information set decoding framework, and this actually brought some improvement. And in particular, so we now have like a kind of, yeah, I tried to simplify the idea. So we have like a layered approach of this algorithm. So we have the information set decoding that creates a subinstance of the problem. Then we use the sieving to solve this subinstance of the problem. And then within the sieving, we are also using the near neighbor search that is quite well developed and advanced. And then we obtain some improvements. In particular, we get very close to the BGM-M algorithm in the asymptotic setting, and even more importantly, we provide better time memory trade-offs, which was like some improvement that was not that commonly seen in this development of the ISD's algorithms, so it can be seen as a very interesting like move toward the practicality. Okay, and one thing to mention also here is that these sieving techniques, like in this approach, is very common in the lattice-based literature. So the question for some people who are familiar with this type of techniques is that how it comes that it was never used in the code-based setting before. Well, people tried, yet it has not worked. And the reason it has not worked was the design of the problem itself, or like the question that we were asking. So as I explained, the code sieving here. So the crucial difference between the lattice-based approach and the code-based approach is that we are now, so in the code-based approach, we are starting with the vectors of a fixed weight, and then we sieve those that are in the code, or sieve out those that are not in the code anymore. In the lattice approach, it goes the other way around. You start with a bunch of lattice vectors, and then you sieve those that are of like too large weight. And that was different approach. And whenever people try to apply this approach in the code-based domain, it has never worked, and it always failed. So this was actually a very important breakthrough in a way. Okay. So finally, I'm coming to summing up, to at least this part. So as I mentioned, yeah, we are interested in how much of the like improvements we are getting in this like very relevant regime. So in the peak of our like curves that correspond to kind of a hardest instances of our problem. And what you can see, so PRONJ is basically the baseline. So it's like gives, yeah, I will give you the values afterwards. So it's a baseline for all these algorithms. And then we have like the first improvement that comes from Doomer and Stern's algorithm. Then we have like the improvements that come from MMT and BGMM that basically use these representation techniques. Then we go to the improvement that comes from the like sieving. And finally, we come to the improvement that it comes from all these techniques combined. Nevertheless, it's not really practical algorithm. So BGMM is something that we look into once we are like deciding on our code parameters. And if you are just interested in this peak part, like this 1 point, like that would probably cut through here, we can also observe only these exponents for this fixed point, basically for the like code rate that is equal to 0.5, and for the weight that basically gives you the unique solution. And in that case, we have like this line of the algorithms and the improvements that we achieved over time. Nevertheless, this line is not quite chronological. So this is basically just like the improvements of the complexity. But if we want to see how it chronologically improved, we can start from PRONJ algorithm, that was the basic one. Then we introduced collisions that correspond to the Stern and Doomer algorithm. We obtained some improvements. Then we introduced the representation techniques that were combined with some of the previous things, but representations were some new thing. And then we like moved farther on the curve. Then, like May-Ozerov introduced the near neighbor search that was also used afterwards in the both May approach along with BGMM. So we obtained the best possible asymptotic running time for now. And finally, we used the sieving combined with the near neighbor search to improve over the most practical algorithm and also to achieve some better time memory trade-off. Yeah.
These are all asymptotics. If I were to implement all of them in practice, how would they actually compare?
So yeah, it's a very good question. So I know just like what is the best one, but I cannot tell you much. I mean, I have not tried to implement all of them. So yeah, it depends also what you want from your algorithm. So if you want like to have like the most memory efficient, that would be PRONJ because it requires almost no memory. And I think that's actually the one that is fairly commonly applied. Apart from that, I think that Stern and Doomer doesn't have like any like very big concerns with the implementation. So they are still like, yeah, like in comparison to PRONJ, they probably don't give you a very huge implementation like advantage. And then when you go farther, like with these like representation techniques and near neighbor search, it can go like actually quite ugly and it can be very hard to implement them. But to be fair, I never actually tried, so I cannot like tell for sure. Yeah. Yeah, so maybe we can have like a 5-minute break or something like that. So yeah, for the rest of the talk, I was planning actually to talk about the quantum ISD algorithms and also to cover like the other type of attacks. But yeah, I think that in the end I will just, yeah, try to, like, I will definitely explain the quantum algorithms, and for the statistical decoding part, we will see how much time do we have, like, and how much of interest do we have, like, in going to more technical details, and at the end we can still maybe try to do some discussion on what would be some ideas for the future research developments in this area. Okay, so for the quantum part, when I say quantum here, I want to actually clarify that it's not like purely quantum algorithms, like the algorithms that Suba like explained to you like 3 days ago were like purely quantum. This type of like what we refer to as quantum ISD algorithms are actually hybrid algorithms, where you have like the classical ISD combined with some quantum algorithms that are solve part of your problem. So in that sense, we can call them hybrid. And as I mentioned, we combine the classical ISD's algorithm with some of the techniques that you have seen before. So Grover search, so that's like a very basic quantum algorithm that actually gives you the first like quadratic speedup. Then the generalization of it is the so-called amplitude amplification that I will also recap like in short. And then finally we go to the quantum walks that can be seen as a further step in the generalization of these quantum algorithms, and it also gives you some, like, at the best you can hope for is quadratic speedup. So none of these algorithms are claiming they are breaking things or like providing some exponential speedups. So all of these things are actually in the whole regime of the quadratic improvements algorithms. Okay, so let's start with first recalling what was the Grover search. So if we have a function that has an efficient classical description, that's a kind of a Boolean function that takes as an input the n-bit string and outputs either 0 or 1. What the Grover algorithm can provide you is that you can find I such that of I is equal to 1. So basically the input that leads to the output that is equal to 1 in time that is polynomial in the input size and multiplied with 2 to the n over 2. So basically, instead of searching through the whole list of all the possible entries to your function, you can search through square root of the full number of these possible inputs, and you will still get the solution. Or the Grover algorithm will tell you that nothing evaluates to 1. Okay. So that's probably that you have seen before. So it basically provides you quadratic improvements in the database search environment. And the amplitude amplification can be seen as a generalization of this algorithm. So you have again a Boolean function f, and you know that there is an oracle or an algorithm A that outputs I such that f of I is equal to 1 with probability p, and that f of I is equal to 0 with probability 1 minus p. And what the amplitude amplification provides you with is that you can find such f of I that is equal to 1 by making 1 over square root of p queries to your algorithm. So this is this is formulated in the query complexity manner. So instead of asking your oracle about 1 over p queries that would happen in the classical case, in this case you can ask for 1 over square root of p queries. And each of these queries also requires some time to be answered, but we are not taking that into account here. Okay, so these are the two algorithms that you have seen before. Regarding the quantum walks, I was thinking about presenting them too, but it would require a lot more time, and it's also it's not super technical, it's just a very it's a topic on its own in the quantum setting. But I encourage you to, if you're interested, to take a look at the so-called MNRS framework. So it comes from the names of the authors, and it's actually the basic literature that you can use for the quantum walks in general. I can also provide you the reference afterwards. So let us recall how the information set decoding looks in the classical setting, or in general, any setting. So we have again, an instance of the decoding problem as the input, and also requiring the solution to this problem in the output. And we have these 3 steps. So the first one is guessing the information set. So this part can then be efficiently in polynomial time, so we don't have the need to actually improve it that much. Then we have solving the subinstance of the problem. So, and the difference in the quantum algorithms is that we are now assuming that we can potentially use some quantum algorithms to solve this subinstance. So we can use the quantum oracle to solve this part of the problem. And then the final part is checking the sub-solutions, or checking the solutions of the subinstance if they give you the solution to the original problem. And one thing that you might have noticed here is that in the classical case, what we used to have was capital N. So you're checking capital N solutions, and each of these checks is done in polynomial time. And in the quantum setting, it improves to go to square root over N. It can be done using Grover search. So yeah, in the end, we again return the solutions that are in the code of the Hamming weight W, and nothing quantum is happening in this final part, so we are actually getting classical solutions to our problem. Okay. So the running time and the memory of this type of the algorithms is very similar to the one that we saw for the classical case. The crucial difference is actually this square root of 1, square root of P1 times P2, where this expression corresponds to the probability of finding a solution. And does anybody can tell me, like, yeah, can you guess where this improvement comes from? So like, instead of having like 1 over P1 times P2, we now have 1 over square root of P1 times P2. Yeah.
It seems like the probability didn't change, but you're checking the solutions faster, right?
Yeah. Yeah, but like which algorithm can you advise to do that? So Grover, in this case, like amplitude amplification, you just observe the whole iteration of your algorithm as basically this algorithm A, and we are trying to amplify its probability of success. And that can be done with like using the like quantum algorithms, and it's a very generic approach. So it's something groundbreaking. It's like a very like standard way to do it. But in the case of the information set decoding, it actually works quite well. Okay. The rest the rest of the things are quite the same, apart from the fact that like now this running time and this like memory is actually potentially quantum running time and quantum memory. So you need to evaluate different type of resources in comparison to what we had before. So now you might need to also evaluate qubits, you might need to evaluate quantum gates and things like that. But the high level idea is the same. Okay, and the first algorithm in this line of the algorithms is the so-called Bernstein's algorithm. It can be seen as like a very straightforward analogy of the initial like classical ISD algorithm. So a quantum equivalent of the Pronge algorithm. And it literally uses the like a Grover search on top of the Pronge algorithm and obtains the quadratic improvements. So it's as simple as it gets. And yeah, so as I mentioned, so in this case also you observe like full iteration of your algorithm as like some output of some algorithm A. And in that case, what you try to improve is actually the number of iterations that you need to run. And in this case, it's going to be 1 over square root of P1 times P2. Okay? And as in the case of Pronge algorithm, so the oracle B in this case is trivial. So it does nothing. Yeah. And then we had like first time we used some non-trivial like quantum oracle in this to solve the sub-instance of the problem in the work by Kachigar and Tillich. And in that case, in their case, they combined this like quantum oracle with Wagner's algorithm MMT and BGMM that you have seen before in the classical setting. And they used like a quantum walk to try to solve this like sub-instance of the problem, and basically quantum walk was this quantum oracle they were using. And what they achieved by using that is that slight asymptotic improvements in their algorithms. It's very hard to argue about the concrete improvements because like quantum algorithms cannot be that easily implemented. So like we are not even trying to discuss that. So asymptotic setting is the one we are aiming for. And we had like some slightly asymptotic improvements with using this quantum oracle. Nevertheless, it comes at a huge memory cost. And I will show you the numbers, and you will see what are the improvements. And then you can just imagine that like you're going from the memory that used to be 0 to something that was like very non-negligible. And then after that, we also had like some further generalization of this approach by Kachigar and Tillich. And in that case, so Kirshanova tried to use near neighbor search on top of these techniques, combine them together to obtain some kind of a May O0 version of the quantum algorithms. And it again provides some slight asymptotic improvements, and again at a very high memory cost. So finally, we obtained something like this. As you can see, like it's quite different from the line that we had like for the classical setting, in which you have like a long line of research, like very different techniques that were used. So here it was mostly like those 2 or 3 techniques that were combined with like some classical ISD algorithms. And every time you basically obtained like an improvement on the, what is that, like 4th or the 5th decimal, something like that. So that's as far as we could go. And every time you increase the quantum memory and even the classical memory quite a lot. And I can also tell that I tried to work on the quantum ISD algorithms, and for us, we didn't even manage to improve at all. So for us, we were as bad as the Bernstein plus Grover. not as bad, as good as this type of the approach, because we tried to combine the sieving, the NNS, and it turned out that it does nothing. So we came to some kind of limit, and we were not able to break it. And for us, the reason was like these constraints that were actually related to the sieving part of the algorithm. But in general, it somehow seems that there might be some issue and some reason why we are like not obtaining like higher improvements in these parts. So one can argue that either we are, maybe not doing the right approach when we are trying to construct this like sub-instance of the problem or advise which quantum algorithms to try to solve it, or there is some inherent limitation in this approach. So I would like to encourage you to try to work on this question because at least for me it's very interesting. Okay. And statistical decoding. I think that like I will just give the very high level overview and without going into technical details. And hopefully if someone is interested really much in this type of the attacks, you can take a look later on in the presentation or also in the literature that I provided here. So statistical decoding is quite different, not very far, but like quite different from the information set decoding. It comes from the observation that vectors in the dual code reveal some bias in your error vector. So in some sense, you can actually try to guess your error vector, but in a very different way from the information set decoding approach. And the search is done in dual code, and I will, in short, I will explain what the dual code means and also what the bias means here. So it falls under this category of dual attacks. And so this is, as Monica has mentioned, this type of attacks are actually quite important. So they're not common in the coding, code-based cryptography setting. Nevertheless, in the multivariate cryptography, for example, similar kind of approach actually led to these breakthroughs. So it is very important to also consider this type, this whole branch of algorithms. And so let's start with what is actually a dual code. So if we are given a linear code C, and we denote by these brackets the inner product between x and y. It's written linear, sorry. It's inner product between x and y. Then the dual code that we denote by C perp is actually given as the old vectors h in fq to the n, that once they are whose inner product with the code words actually gives you 0. And as you can see from the definition, so the dual code is another linear subspace of the vector space fq to the n. The dimension of this vector space is actually n minus k rather than k that was in the case for the linear code C. And what we can also observe here that is relevant also for the statistical decoding algorithm that I'm going to describe is that if you have some noisy code word C tilde, that basically comes from the code word with added error, then once you multiply this noisy code word with the dual code, what you obtain is the inner product between the code word and this dual vector, which by definition is equal to 0. So this term diminishes, and what remains is basically this inner product between the error vector and the dual vector. Okay, so it's going to be relevant for the algorithm that I'm going to describe now. So in the statistical decoding setting, we are again given the instance of the code word finding problem, and I denoted by EI the positions in your error vector. And this notation here basically means that you have values from 0 to n minus 1. And what we want to do now is to actually output the first n bits of our vector rather than the full error vector. So basically these positions EI in the range from 0 to n minus 1. And the way it is done in the statistical decoding setting is the following. So we know that there will be, to do so, we know that there will be 1 over epsilon square iterations that are necessary to be performed in order to be able to actually produce these first m positions of the error vector. And I will explain what epsilon means slightly later. And we start by sampling the dual vector, so H, that is of the weight W in this like dual code, and we separate the first part of this error vector and denote it by HS. This comma means concatenation, and then like we have like HN. So these are basically first and the second parts of your dual code. This can be done efficiently in polynomial time in n, and then we calculate what we can basically see as an LPN sample. So we multiply this C tilde with like this vector, like dual vector H, and what we obtain, as we saw earlier, is basically the multiplication between E and H. We will not know what is the E, but we know what is the inner product between the two. And we can separate, by definition, we can separate this into two parts, like the sum that depends on the first m bits and the sum that depends on the last n minus m bits. And that way, so this can also be done in some time that is polynomial in n. And what we obtain that way is basically an instance of the LPN problem that we can then try to solve to obtain the first m positions of our error vector. Okay? This is the basic approach. And what we know is that since like the running time of like, those two parts is very efficient. So basically what determines the running time of the whole algorithm is the number of iterations that is given by 1 over square root of epsilon and the cost of the part that solves the LPN. The memory is also like proportional to the number of iterations. And so this value epsilon is basically something that we call a bias, and it can be calculated as based on the distribution of this like second part of the inner product that we can determine in advance by knowing like how do we sample this HN. I will not tell you more details on that part, but in fact we can actually like calculate what is this bias epsilon. And we know that it's some function that goes like, that is exponential, like inverse exponential in a sense, in n, like the code length, as well in the weight of the error vector, as well in the weight of this HN part. So otherwise, if it was not like that, so this algorithm would be like very efficient. So it would mean that like we can solve the code word finding problem like in, for example, polynomial time. So if this E was big enough so that we get something that is very close to 0 in this case. In that case, our algorithm would run in constant time, and that's something that we cannot expect in the setting that we are observing. Okay. So yeah, the first algorithm was using so the first algorithm in the line of the statistical decoding is the one by Jabri. I hope I'm pronouncing it correctly. So it considered like a very simple case where we are just trying to find the first bit of our error vector. And in that case, like this part that I referred to as solving the LPN instance was done basically just using majority voting, so very simple approach. Nevertheless, the epsilon was very low in this case, so the bias was very low in this case, so we didn't obtain any improvements of the over the information set decoding algorithm. And the first true improvement actually came from the approach that was presented by Carrier and et al., where they managed actually to outperform the ISDs, but for certain parameter range. So now, like we used to talk about like the generic algorithms that work the best in all the possible like ranges. But now we actually obtained an algorithm that for a certain specific range, for the code rate that is smaller than 0.3, actually performs better. And it was a major breakthrough because like in the whole history of ISD, like more than 60 years, there was no like such a big breakthrough. And then like it came, at least for this restricted parameter regime, it came with the statistical decoding. And the improvements are like due to different factors. The first one, we increased this parameter m and then decreased the number of necessary iterations. Then so the authors also used the fast Fourier transform in the like as a subroutine in this like when they are searching for the solution to the LPN problem. And finally, so yeah, this actually significantly reduced the running time of this part. And then they also used some techniques that were also used in the ISD to enumerate the second part, not the solving the subinstance, but enumerating the second part and also creating like a smaller number of necessary like iterations for calculating the error term of the LPN sample. Okay, yeah. I hope that yeah, you still bear with me. So some concluding remarks. So yeah, today we talked about the information set decoding framework and is the best generic attack against the decoding problem in the Hamming space. It relies on the guessing of the information set and then using some like more advanced techniques to solve the rest of the problem that remains after guessing part. And I also briefly spoke about the statistical decoding attacks that are the best attacks for this like low code rate regime. And in this case, we are not actually approaching the problem directly, so we are not directly aiming to like solve or find the parts of the error vector itself, but then we are trying actually to do that in the dual code. So we refer to this type of the attacks as dual attacks. And the question now is like, since we have like so many of the algorithms that are like doing kind of like variations of the information set decoding, so what can we expect to appear next? So some of the techniques that I described actually drew this, took their inspiration in the lattice-based domain. And as I mentioned, the sieving, in particular in the locally sensitive filtering that used as a part of the sieving, came from the lattice-based cryptography. So the question now is like, is there more techniques that from the lattice-based cryptography that can be used? And in particular, one line of research that can go in the direction of the basis reduction techniques that are very common in the lattice-based setting, not yet in the code-based setting. They are not that well explored. There are some papers on this topic, and I'm actually quite interested in this line of research. But yeah, so the question is like how much we can achieve with this type of techniques. And also another thing is that, yeah, now we were trying only to use this subset of the quantum algorithms that can provide us with at most quadratic speedup. The question is it possible to somehow also use this other branch of the quantum algorithms that are relying on the period finding that can provide us like some exponential speedups, at least in certain parts of our subinstance. The intuition probably tells you that it will be too much to expect that there will be some quantum algorithms in that part of the field that would actually provide you sub-exponential running time of the quantum algorithms. Because so for this type of algorithms, what you need is certain amount of the structure. So what Suba explained was you saw the Deutsche-Josel algorithm. I think that, yeah, she also talked about Simon's, maybe. FFT type of the algorithm, so they really require some kind of a promise that you need to have. In this case of decoding problems, you don't have much of a promise, so it's very hard to exploit any kind of structure. So yeah, the question is there any hope of trying to obtain this type of the algorithms? And yeah, for the end, yeah, again, I would like to acknowledge ChatGPT for my beautiful pictures. Yeah, it's actually, yeah, it gave me a slightly harder time for this other presentation. It was not very easy to convince it to go on the certain parts of my graphs, the points I wanted, but still it helped a lot. So yeah, and thank you for your attention.